exercises class. But today we will continue with the solution of exercise 1A and see if we are able to solve question 9, question 10, and then question 11. So my name is Sheldon, a PhD student in the Department of Mathematical Science, Indiana University, Indianapolis. Alright, so question number 9. We have suppose function f and a to b is a Riemann integrable. Then we have to prove that if c, d belongs to R and then a is less than c, less than d, less than or equals to b, then f is Riemann integrable on c, d. So that is, we have our function in this form. So we have a and then we have b. So we have c, then we have d here. So we want to check if we restrict our function on c and d, will it still be Riemann integrable on this point. So then let's prove this. So we have since f is Riemann integrable and a, b. So that means that for any external greater than 0, there exists a partition. There is a partition P on a, b such that the difference between the upper Riemann sum and the lower Riemann sum can be made small epsilon. So we need to define a partition on our c, d. So let's assume that this black line is the partition of P so there is a partition of P, then we cannot define another. So assume that the partition P of a, d includes c, d. So that means that our partition is fine. So let's use the word if the partition P of a, d includes c, d, so that is fine. And then if not, so we can define, let's define a partition P prime of, so this a, b, a partition P prime of a, b that includes c, that include the point c and d. So for that now, so this still holds. So partition f a, b prime minus n of this. So you can verify this by using the refinement of the partition. So the lower Riemann sum of the refinement of partition will increase while the upper Riemann sum of the refinement partition will decrease. So that's the odd. So now we can now take, so let P CD be a partition, be a subset partition of P prime that contains points C and D. So since this partition is a subset of our P prime, then the upper Riemann sum of C, D and P prime of C, D, the difference of these two guys of this will be less than or equal to at most the difference of this big partition. So, and this is less than epsilon. So that implies that f is Riemann integrable on C, D. So the key here is that the partition C, D is just a subset of partition P prime. So the difference between the upper Riemann sum and the lower Riemann sum over this small interval will be less than or equals to the difference between the upper Riemann sum and the lower Riemann sum of this big interval, and that concludes that proof. So question 10, we have suppose f over bit to r is a bounded function and C is an element of A, B, and their inside we have to prove that f is Riemann integrable on A, B if and only if f is Riemann integrable on AC and f is Riemann integrable on C, B. And furthermore, you have to prove that if these conditions holds, then integral of A to B f is equal to integral of A to C f plus integral of C to B. So that means that we're proving almost three things. So if we look graphically, we have this. So assume that our functions of this form, then we have A to B, so we have C here to B. So the area under this down here, and then from this point to that point, it's just the sum of these two areas. So, and that is what you want to prove. So let's first of all put the forward direction. If f is Riemann integrable, then f is Riemann integrable on A, comma B, then case 1, f is Riemann integrable on A to C. So let's first of all prove this one. So for any epsilon greater than 0, there exists a partition P A comma B such that the difference between the upper Riemann sum of A comma B, P A comma B, and the lower Riemann sum A comma B, P A comma B is less than epsilon. Since f is Riemann integrable by this oath, since f is Riemann, we assume that f is Riemann integrable on A comma B. So let's now define another partition in order to prove that case 1. So let P A comma C be a subset partition of alright, so let's define another partition. So partition this may not necessarily include C, point C. So if we define another partition, let P prime A comma B be a refined partition of B, partition P A comma B that includes point C. So in whatever cases, the upper Riemann sum of this with the new partition will still be less than epsilon. So you can also check that out. So now we can now define a partition. So let P A comma C be a partition, be a subset be a partition. Okay, let's say be a subset partition of P prime A comma B that includes point C. So that means that since AAC subset of P prime A comma B, then the upper Riemann sum, the difference between the upper Riemann sum now on A comma C, P A comma C minus the lower Riemann sum A comma C, P A comma C will be less than the upper Riemann sum of A comma B, P prime A comma B minus the lower Riemann sum F A comma B, P prime A comma B. And since this guy is less than epsilon, so that implies f is Riemann integrable on A comma C. Similarly, for case 2, that is for case 2, that is f is Riemann integrable on C, B. In other direction now, so you can also prove that. So in other direction, if f is Riemann integrable on A, C, so that means for any external greater than 0, there exists a partition P. Is the partition P such that the upper Riemann sum of f is a partition P A, C, AC, P of A, C minus f A, C, P of A, C is less than epsilon. And then similarly, if f is Riemann integrable on C, B, so that also implies that UF A, C VAC minus this guy also, so that is C, B, C, B, of C, B is also less than epsilon. So now we can now divine. So let P, so let P be the common refinement partition of A, C, or this should be A, B, C, B, A, C, partition of B, A, C, and partition of C, B. So that means that the partition, the upper Riemann sum of f so that means that the upper Riemann sum of f of b of A, B difference with f b of A, B will be less than or equal to the sum of these two guys. So here we can make this one xn over 2. Then we have union of f A, C, we have A, C, so we have f A, C, then partition of A, C, because all this that may not necessarily be true. But you know that since P is a common refinement, that means that the lower partition of P A, C, F A, C, P A, C will be less than N F A, B, P less than the upper Riemann sum P, and this will be less than the upper Riemann sum. We have this theorem in our first video. You can check it out. A comma C. Similarly, this also holds for N F A C comma B of XC is less than N F A comma B of P less than UF A comma B P less than UF A comma B and P of what? So this is C comma B, C comma B, P of C comma B. So by the time you with this, by the time you sum up these two, so by the time you sum up these two, then you are going to have, and with this one, let me list this with these properties: 1, 2, 3, and then 4. So that implies that the lower Riemann sum of A comma B, sorry, the upper Riemann sum A comma B, P minus the lower Riemann sum of A comma B of P is less than epsilon, and hence F is Riemann. F is Riemann integrable on A comma B, and that completes that part. In the same vein, for the second part, you can also make the same. You can also make the similar arguments. So to prove, so you can also prove A comma B of F is equal to AC F plus CB of F. So this also follows from 4 point star 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 star. So this also follows from the point star 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 star. Okay, so let me see if you can check one more question. All right, so let's check one more question. That's question 11. We have suppose F A comma B mapped to R is Riemann integrable. So we define F such that A comma B R by F of T equals to 0 integral AT F, this is if T equals to 1A, and then if T belongs to A comma B. So we have to prove that F is continuous on A comma B. So what we need to show, so we need to show that 1, F is continuous, F is continuous at T in entire of A comma B. So 2, F is continuous at the end point of A, and then 3, F is continuous at the end point of B. Okay, so these are the three cases we are going to consider. So we are going to use using the definition of continuity and then properties of Riemann integral. So let's check the first case. Case 1, if T is in AB. So they have something like this. We have A, B, and then we have our T. Then we can have, and our function is continuous. I want to check out if our f is continuous at that point. So we can just get a small h. Let h be small such that T plus h still belong to A, B. So we get a point that is not far from T. Let's make it here. So, and that point is h. This point we have h. So this point will be T plus h. Okay. So that means that we want to check. So we need to check we need to show that f of T plus h minus f of T as h tends to limit h tends to 0. This guy is equals to 0. So let's show that. So by the definitions of our f of th, we have is given f of t equals to 0 if t equals to a and is equals to a to t. If we have this condition, that means that for f of t, for this case we have a to t plus h of f minus for t we have a to t of f. So if we check this, if we subtract the integral from a to t plus h, so from here to here, then if you remove from here to here, so we'll be left with t to t plus h. Okay, so you can carefully check that. So we have t to t plus h f. Then we can now bound these guys. Okay, so since f is Riemann integrable by assumption or by the hypothesis, then for n in x greater than 0, there exists a delta greater than 0 such that t plus h of f is less than m and the length of t plus h minus t. Okay, the m is the bound of f. Alright, so and that means that our mod of ft plus h minus f of t is less than or equals to m mod of h. So if we take the limit as limit h tends to 0, so this limit h tends to 0, so this equals to 0. So thus limit h tends to 0 f of t plus h minus f of t is equals to 0, and this implies f of t limit h tends to 0 ft plus h is equals to 0. So f is continuous and at t belongs to a comma b. So in the interior we see that f is continuous. So for case 2, so I want to show continuity at t equals to a. So as t tends to a, so assuming we have this, so we have our function, we have our a, b, and t is moving to a. So we want to check if our function is also continuous at that endpoint. So that means that we want to show that the limit of t tends to a f of t to a is equals to f of a, if I'm correct, sorry, f of t equals to a. So here now, so for t greater than a, then we have this function f of t minus function f of a, and that's equals to integral a to t by the definition, integral a to a, and that is equals to 0. Remember that, and this is equals to the bound of t of a, and then by the properties, this is less than or equals to m a, sorry, t minus a. So by the same condition we stated in case 1, so that, so as limit t tends to a positive, so you observed that this also equals to 0. So that means that our function f is also continuous at t equals to a positive. So now the last one is continuity at t tends to b minus. So we have this a, b, so our t when t is moving to these guys, so we want to check the continuity of the function and that end point. So for here now, for b less than, sorry, for here now our t is less than our b, so we have f of b minus f of t. So by the definition we have integral a to b of f minus integral a to t. So if you observe here from here to here h to b, and you subtract from here to here h to t, so you'll be left with t to b. So that means that we have mod integral t to b of f So by the same thing, we can also bound this just with the m, which is the bound of f, and then the difference of the interval. Then we have, so you also see as t approach b negatively the back, so we have this condition, so equal to 0. So for those three cases now, you can conclude that f is continuous on a, b, and that ends our proof. So in the second video, we tried to check problems 13 to problem 12 to 13 to 14, and then we'll move to another section. Thank you for watching. Hope to see you in the next video.